Good afternoon and welcome to your science review with Mr. Blades. Today we're going to be going over our constant acceleration review. Let's get started. A water balloon is dropped from 6.75 meters. How long will it take to fall? And how fast is it going right before it hits the ground? Let's work this out together. As we discussed, the water balloon will take 1.17 seconds to fall, and in that 1.17 seconds, it will accelerate to a velocity of negative 11.48 meters per second. Now, let us use the information from the last slide to graph our position, velocity, and acceleration versus time graphs. But before we do that, let's think about it. The position of the water balloon approaches zero from the very top. We had an initial height of 6.75 meters, and it fell towards the origin at the ground. It accelerated towards the ground, so we would expect that line to get steeper. For the velocity versus time graph, since the acceleration due to gravity doesn't change, we would expect the velocity versus time graph to have a constant slope or be a straight line. Finally, the acceleration versus time graph would reflect that the acceleration due to gravity does not change and be a horizontal line at negative 9.8. Let's see if that's what it turns out to be. As you can see, our graphs conform to what we would expect to see. Our velocity shows us on a negative velocity, which means we're approaching or coming towards the origin with a negative velocity, and a acceleration that is causing our water balloon to fall faster and faster. Next, we can see that our acceleration is on the negative side of the x-axis and negative side of the y-axis and has a value of 9.8 meters per second squared. And finally, we can see that the position graph starts above the origin and approaches the origin with a line that gets steeper and steeper. Now let's define these terms. Acceleration is the change in velocity divided by time. Next, free fall is any time an object is falling under only the force of gravity, not being pushed, not being pulled, only being brought towards the ground by gravity. And lastly, Galileo's law of falling bodies. We talked about this in the very first lecture, but Galileo's law of falling bodies is that everything falls with a constant acceleration near the surface of the Earth. The velocity of the object falling towards the ground varies with the square of time, meaning that it accelerates. So what are the three types of acceleration? Positive, negative, and zero. By looking at your numbers for velocity and acceleration, how can you tell if you're speeding up or slowing down? If the signs for velocity and acceleration are the same, that means they're speeding up. If they are different, it means they're slowing down. So if you have one positive and one negative, you're slowing down. If you have both positive, then you're speeding up. Can you have acceleration and zero velocity? Yes, because you can accelerate through a zero. Like when you throw an object straight up into the air, it is always accelerating towards the ground, even though it will stop briefly at the very top before it turns and comes back. Can you have velocity and zero acceleration? Yes, a constant velocity has zero acceleration. And can somebody have positive acceleration and be slowing down? As we discussed before, the signs of the acceleration and velocity are what determine whether or not you're going faster or slower. So a positive acceleration and a negative velocity would have you slowing down. So let's take a look at these graphs. What's happening? Well, the first graph looks an awful lot like what we drew for dropping our object. So it's an object approaching the origin at an increasing speed. Next, we have an object going away from the origin with an increasing speed. You can tell its displacement is getting more positive and is getting steeper. And then lastly, we have an object traveling away from the origin with a constant velocity. Same deal for our velocity versus time graphs. Remember, positive velocity is moving away and negative velocity is moving towards the origin. So in the first graph, we have moving away from the origin, getting faster. And the second, we have moving towards the origin, but getting slower because our velocity is getting closer to zero. And then lastly, we are moving away with a constant velocity. A car can accelerate from a rest to a speed of 28 meters per second in 20 seconds. Our acceleration is 1.4 meters per second because our change in velocity is 28 divided by our change in time, which is 20 seconds. What is our displacement? If we just employ our displacement equation, delta x equals 1/2 a delta t squared, we can have our delta x is equal to 1/2 1.4 times 20 squared, which is 280 meters. Likewise, using information from the last slide, let's graph our position, velocity, and acceleration. Again, let us talk briefly about what we expect to happen. We have an object that is accelerating, getting faster and driving away from the origin. So we would expect our position versus time graph to show that the position is becoming more positive and the line to get steeper and steeper. Next, since we have a constant acceleration, we would expect the velocity versus time graph line to be straight, but to be on the positive side of the graph and increasing in value. Lastly, the graph of the acceleration versus time graph should show a positive acceleration, so on the positive side of the y-axis, and it should be flat since the acceleration isn't changing. And this is exactly what we see. In a vacuum, which falls fastest, a bowling ball or a feather? They would fall the same because without air resistance, everything falls at the same acceleration. When working a free fall problem, what are the two things we are given to start with? The initial velocity is 0, and our acceleration is that which is due to gravity, negative 9.81. If your velocity is negative and your acceleration is negative, then you are speeding up. Using a velocity versus time graph, how can you find acceleration? You take the slope of the line. And using a velocity versus time graph, how can you find displacement? You calculate the area between the curve and the x-axis and add them all together. On a position versus time graph, the slope is equal to the velocity. On a velocity versus time graph, the slope is equal to the acceleration. This is because the slope shows you how fast something is changing. And the rate of change of position is the velocity, and the rate of change of the velocity is the acceleration. The area under the graph for a velocity versus time graph is the total displacement. And the area under the graph for an acceleration versus time graph is the average velocity. A ball is thrown vertically upward and is caught in the same spot. Is the velocity speeding up, slowing down, or 0 when he throws the ball? The velocity is slowing down. What's the velocity at the top? At the very top, the velocity is 0 as the ball stops and turns back. Is the velocity speeding up, slowing down right before he catches the ball? It's speeding up because now the velocity and the acceleration are both in the same direction. What is the acceleration at the top? Just the acceleration due to gravity. And what's the acceleration right before he catches the ball? Same. The acceleration during free fall does not change. A bus moving at 20 meters per second accelerates by negative 4 meters per second squared. How long does the bus take to stop? Using our delta V equals acceleration multiplied by time, we can solve for a time of 5 seconds. And further, noting that our final velocity is 0 because the object is stopping. We use our displacement equation, delta x equals initial velocity multiplied by time plus 1/2 a delta t squared, and we can find that it's 50. Again, let's do our expectations for the graphs. Since the object is slowing down, we would expect the line on a position versus time graph to show that it is still getting away from the origin, but is slowing down. So we'd expect the line to flatten out. Next, the velocity versus time graph should show a straight line since we have a constant acceleration, but it should be a positive velocity approaching 0. Next, our acceleration versus time should show a horizontal line at -4 meters per second. Let's see. There we go. Everything looks good. For these last few, we will discuss them briefly, but I'm going to leave the math to you. Alex wakes up late for his bus. He's walking to the bus stop at 1.5 meters per second. He sees the bus move faster at 5.5 meters per second. The bus is 100 meters away and it leaves in 30 seconds. Does he catch the bus before he leaves? All right, so what we have is an initial velocity of 1.5 meters per second, a final velocity of 5.5 meters per second, and a delta x of 100 meters. Okay, we need our time to be less than 30. Using the equation at the bottom, which is just combining the displacement equation and reorganizing it so that we solve for t, we can figure out if our time is less than 30 seconds. And we can see that it is in fact 28.6 seconds, and so he does catch the bus. Again, a race car travels at a distance of 500 meters, that's our delta x, while the parachute stops it at a rate of -5 meters per second squared. That's our acceleration, and we already know our final velocity, which, since the car is stopping, is going to be 0. Again, I'm going to allow the math up to you guys so you can get some practice. But our answers are 70.7 meters per second and 14.1 seconds. But let's go ahead and discuss one last time our graphs and what we expect them to look like. Okay, so our car is slowing down and eventually stopping. So our position versus time graph should again show a line on the positive side of the graph, but flattening out. Our velocity versus time graph should show a negative slope of 5 meters per second squared with a positive velocity headed down to 0. And then our acceleration versus time graph should show a horizontal line at -5 meters per second. And that's what we've got. If you're in K, feel free to go ahead with this. And if not, you can turn this off now. A toy rocket is shot straight up into the air with an initial speed of 45 meters per second. How long does it take to reach its highest point? We just use delta V equals A delta T. We know our final velocity at the very top is going to be 0. So how long does it take for the acceleration due to gravity to eat 45 seconds? What is the rocket's highest point? We just use our delta x equation for that. And how long is the total rocket in the air? This is 9.2 seconds because it takes 4.6 to go up and it takes the same amount of time to come down. So 4.6 plus 4.6 is 9.2. What's the rocket's velocity right before it hits the ground? You don't even have to do any math for this one. It is exactly the same as the initial velocity, just in the opposite direction. I hope this was helpful, and I'll see you in class.